Saturn has a hexagon at its north pole. Not 6 mountains, not a camera illusion. A moving storm wider than 2 Earths holding 6 clear sides while the entire planet spins underneath it. The same shape appears inside beehives, snowflakes, aircraft panels, and the graphite in your pencil. The usual explanation is simple. Hexagons are efficient. Fine. That explains the bees. It does absolutely nothing for a gas giant made of moving clouds. So why do systems with different materials, different sizes, and completely different rules keep ending at 6 sides? We can start with the example that seems easiest. The beehive.
Let's pack equal circles side by side and small gaps appear between them. Those gaps cannot store honey. Fill them with wax and the hive spends extra material solving a problem the shape created. Excellent alone, difficult in a group.
So forget circles for a moment and try regular polygons. Pentagons leave gaps. 7-sided shapes leave gaps. Octagons can cover a surface only when smaller shapes are added between them. There are just 3 regular polygons that can tile a flat surface entirely by themselves: equilateral triangles, squares, and hexagons. All 3 can divide a hive into repeating cells, but they do not require the same amount of wall. For equal areas, triangular cells need the most boundary. Squares need less. Hexagons need less again. That means fewer shared walls for the same amount of storage. Less wall means less wax. Less wax means more of the colony's energy can go into honey instead of packaging. And there is another clue. Take equal circles and pack them as tightly as possible. Each circle ends up surrounded by 6 others. Connect their centers, and the same 6-sided pattern appears. The hexagon gives the hive something close to the roomy efficiency of circles, without leaving unusable gaps between them. At this point, we seem to have the answer. Hexagons appear because they pack space well. Then Saturn ruins it. After Saturn's north pole, a fast jet stream circles the planet in the shape of an enormous hexagon. Each side is roughly as long as Earth is wide. The whole pattern stretches close to 30,000 kilometers across. And none of the honeycomb logic applies. There are no storage cells. There are no shared walls. No wax is being saved. Nothing is being packed together. The entire shape is made from moving gas. So this hexagon has to come from motion. The jet stream moves at a different speed from the atmosphere around it. When neighboring flows move at different speeds, waves can develop along the boundary. Picture a circular current with a repeating wobble running around it. Under the right conditions, that wobble can become trapped rather than drifting away. The wave keeps traveling around the pole, and its broad bends produce the corners we see. The hexagon is not a solid object sitting inside the clouds. The gas is constantly moving through it. The pattern survives because the flow keeps rebuilding it. Scientists have produced similar polygonal shapes in rotating fluid experiments. Change the speed and the conditions, and the flow can settle into triangles, squares, hexagons, or other patterns. Saturn did not build a honeycomb. Its atmosphere found a stable wave with 6 bends. Which means our first explanation was too small.
A honeycomb becomes hexagonal to reduce wall. Saturn becomes hexagonal because of a rotating wave. Snowflakes get there through another route. When water freezes into ordinary ice, its molecules settle into a crystal structure with 6-fold symmetry. Long before a snowflake is large enough to see, the directions in which it can grow have already been set. More water molecules attach to that tiny crystal. The crystal expands outward along those preferred directions, and 6 main arms begin to appear. The details depend on the journey. A falling snowflake passes through regions with different temperatures and different amounts of moisture. Those changes affect how quickly its edges and tips grow. One flake becomes thin and simple. Another develops branches, plates, or needle-like structures. Yet the main 6 directions remain because they come from the crystal lattice underneath. Sometimes a flake appears to have 12 arms. Usually that is 2 6-fold crystals growing together at an angle. The cloud can decorate the shape almost endlessly. It does not get to renegotiate the underlying geometry.
Now take an ordinary pencil. The dark material inside it is not lead. It is mostly graphite, made from carbon. Inside graphite, carbon atoms join into flat sheets of repeating hexagons. Separate one of those sheets from the stack, and you have graphene, a material with exceptionally strong bonds across the sheet. That sounds slightly ridiculous when the material in question can be rubbed onto paper by a child. The trick is that graphite has two very different kinds of strength. Within each sheet, the carbon atoms are held together strongly. Between one sheet and the next, the attraction is much weaker. When the pencil moves across paper, thin layers slide away from the stack and cling to the surface. Strong floors, terrible staircases. The hexagonal pattern gives the carbon sheet strength across its surface. The layered structure allows those sheets to separate. Once again, 6 sides appear. But this time there are no bees minimizing wax and no atmospheric waves circling a planet. The angles of carbon bonds lead there on their own. Okay, engineers often use hexagons for a more deliberate reason. Take a thin sheet of material. On its own, it bends easily. Move 2 thin sheets apart and connect them with a lightweight honeycomb core. Now the panel becomes much harder to bend, even though most of the space inside it is empty. The outer sheets handle much of the pulling and compression. The honeycomb core keeps them separated and transfers force between them. That gives the panel thickness and stiffness without filling the entire interior with solid material. This is especially useful in aircraft and spacecraft, where unnecessary mass creates an immediate chain reaction. More weight requires more fuel. More fuel adds more weight. Then stronger components may be needed to carry both. A lightweight honeycomb panel helps stop that argument before it begins. The bee uses hexagonal cells to save wax. The engineer uses them to save mass. Similar geometry. Different bill. Fast, punchy. Hexagons also solve a problem that has nothing to do with wax, atoms, or structural panels. Movement. On a square grid, moving from the center of one cell to the cell directly beside it covers 1 unit of distance. Move diagonally, and the real distance is longer, about 1.414 units. Many games still charge 1 move for both journeys, and trust that nobody at the table brings a calculator. A hexagonal cell has 6 immediate neighbors. The center of every neighboring cell is the same distance away. There is no special diagonal direction that quietly gives a player extra distance for the same price. That is why strategy games often use hexagonal maps when direction and range matter. Squares are still excellent for buildings, screens, floor tiles, and spreadsheets. Their diagonals are simply under investigation. Now, put the examples together. The honeycomb comes from reducing shared wall while filling a surface. Saturn's hexagon comes from a wave trapped inside a rotating jet stream. A snowflake inherits 6 directions from the molecular structure of ice. Graphite gets its hexagonal sheets from the way carbon atoms bond. Engineered panels use the grid to gain stiffness without filling the structure with solid material. Hexagonal maps give each cell 6 equally distant neighbors. These systems are not copying one another. Most of them are not even solving the same problem. That is the part the easy explanation misses. There is no single law saying that nature prefers hexagons. Instead, 6-sided patterns happen to work well under several different sets of constraints. Hexagons can cover a flat surface without gaps. They can place 6 equal neighbors around one center. Their connected walls can spread force through a network. And 6-fold patterns can also emerge from particular bond angles or repeating waves. Different roads keep ending in the same place. Bees, ice, carbon, and Saturn are all following their own rules. The bee does not know the geometry of a snowflake. A carbon atom has never studied a honeycomb. Saturn is not trying to save construction material. But when a system is pushed toward even spacing, low waste, balanced force, or stable symmetry, 6 sides often become one of the available answers. That is why hexagons can look planned even when nobody planned them. The honeycomb was built. The aircraft panel was engineered. The snowflake, the carbon sheet, and Saturn's storm simply followed their constraints. And somehow, across distances ranging from individual atoms to a storm wider than 2 Earths, those constraints keep drawing the same shape. 6 sides.